Okay, we'll resume our class here. And so prior to the break, we learned about sampling distributions. And one of the big things, and I didn't call it this, but a big concept is the central limit theorem. Okay. And the central limit theorem is the idea that the sampling distributions end up having the normal distribution. Okay. Sampling distribution will follow This is kind of the loose idea here, okay? But so we established that even if the population is not normal, so even if the population is not normal, as long as we're taking random samples with a large enough n, with a, large enough n, so large enough sample size, the sampling distribution of y bar follows the normal distribution. So this is actually a rather surprising, or not surprising, but well, I mean, it is kind of surprising, and it's very critical, and a lot of our statistical inference methods hinge upon the central limit theorem. Okay, and so we had those conditions. Okay. So let me just review some conditions for the central limit theorem. Okay. And so one is that our samples are going to be treated as random samples. Okay, so we have to be able to assume that our samples are random and that the individuals are selected independently of each other. Okay, samples are selected randomly. And individuals are selected independently of each other. Okay, so as soon as you start taking samples that aren't random, the concepts behind the central limit theorem fall apart. Okay. We have samples, and kind of going along with selected independently is the samples are not too big. Okay, we rarely run into this problem, except when our population is very small. Okay, so this is usually not a problem, but what we mean by samples are not too big, general rule of thumb is the sample is less than 10% of the population. And the reason being, or unless you're taking samples with replacement, then your samples can be as big as you want. But the idea being, if you have a deck of cards, in the beginning, 26 are red and 26 are black, okay? And when you draw one card out, let's say it's a red card, then what's remaining is you got 25 red cards and 26 black cards. And, the difference that pulling one card makes is not a huge deal. But let's say you've taken out 10 cards, okay? Then what remains in the deck could be significantly altered by what you've already selected. So that's why we say don't take samples larger than 10% of the population, because then you start messing with the idea that the individuals are selected independently, meaning once you select too many of one or another, it increases the probability of other individuals being selected from the population. So, but again, this is rarely. Generally, when you define a population, the population is very big. So this is usually not the problem. The problem that we generally are concerned about is the samples are not too small. Okay, and again, it's this. We've already covered this rule. If the population is normal, any sample size is fine. And if the population is not normal, generally samples of size 25 are recommended, but extreme skew in the population might require samples larger than 25. N greater than or equal to 25 is usually okay. Sometimes larger N required. Okay. But the central limit theorem, sampling distributions will follow the normal distribution. As long as these conditions are met, so as long as we're taking samples randomly and they're not too small and not too big, which is rarely the case, that they're too big, the sampling distribution of y bar will follow the normal distribution. Okay, so that's a useful thing to keep in mind. Okay, and so now we are going to do our first application of this. Okay, and so if you recall the kind of the map that I made for our class, I don't know if you talked about topics. We started off with data description. That was our first week, and then we went into probability, and then we went to probability distributions, which was the normal distribution, the binomial distribution, and then we went into sampling distributions, which we did today. Okay, and so now we're going to bring together data description and our understanding of probability, which developed into probability distributions and sampling distributions, into statistical inference. So this is our first application of statistical inference, and so our first one into this field is confidence intervals. Okay, and so this is the premise that we are going for with confidence intervals. Okay, so with a confidence interval, we have a sample. Okay, this is what we have. This sample has been selected randomly from the population. Okay, and we'll say the sample has a mean of y bar. So let's say we're looking at IQ scores. Okay, so let's say the sample has a mean of y bar equal to 104. Okay, and the sample has a standard deviation of S equal to, let's say, 13.6. Okay, and there are n equal to let's say 10 in the sample. Okay, so what we have is a random sample of 10 people. The mean is 104. Standard deviation is 13.6. Okay? So this is the data we've collected. Based on this data, what can we say about the population? This is what we want to know. Okay? And specifically, what can we say about the population mean? Based on this data, about the population. Okay, specifically, what can we say about the population mean? Okay, and so this is our first entry into statistical inference, and this is what I said is why we study statistics, is that we want to be able to make conclusions from limited data. Okay, so we can't observe the population directly. It's too big for us to do that. So instead we study a sample, and based on this sample we want to say something about the population. And so here's our first example. We've got a sample. It's selected randomly from the population, and we want to know what can we say then about the population. Okay. And so this is all the information that we really have from the sample. Based on this, what can we say about the population? That's where we're going. Okay. So put this, table this in your head, and I'm going to talk about something else as kind of an illustration as to what we're doing. Okay, so just imagine somebody posts this picture. Okay, so let's say there's a picture and it's on a football field, 30-yard line of the football field, and what it is, it's a picture of a doggy at the 30-yard line, okay? All right, and then it has the caption, dog at 30-yard line, but then it says, where is the owner? Hashtag he's invisible. Hashtag invisible leash. Also invisible leash. All right, this is ridiculous, but let's go with it. Okay, so there's an invisible man giving his visible dog a walk, okay? So invisible man with invisible leash. I guess an invisible woman is also possible. Invisible man with invisible leash giving his visible dog a walk. Okay, and we see the dog at the 30-yard line. Okay, so we know a few things about the behavior of the dog and the leash. Okay, so we say the leash is elastic. And could potentially stretch very far. Okay, but we also know the dog does not like to strain hard against the leash. Okay. And in fact, about 68% of the time, the dog prefers to be within 1 yard of the owner. And about 95% of the time, dog prefers to be within 2 yards of the owner. And about 99.7% of the time, dog is within 3 yards of the owner. Okay, so you know, it is possible the dog could be more than 3 yards away from the owner, but it doesn't happen very often. Okay, the dog doesn't like to pull against the leash that hard. Okay, so based on this information, and we see this picture was taken, and we see the dog at the 30-yard line, where can we say the owner is located? Or what can we say about the location of the owner? So maybe because the leash is potentially could potentially stretch very far, we can't pinpoint the owner of the location. Okay, and we can't even say, I know for a fact that the owner is, you know, even in this range of the dog. But we can say something like, I am 95% confident that the owner is located where? Between where and where?
28, 32.
Yeah, between 28 and 32. Between the 28 and 32 yard lines on the field, okay? Because even though the owner is invisible, we understand the behavior of the dog, and so we can make a statement like, I'm 95% confident that the owner is between 28 and 32, because we know the dog doesn't like to stray more than 2 yards from the owner 95% of the time. Okay, or, you know, if I wanted to lower my confidence, if I'm okay with only being 68% confident, I can say I'm 68% confident that what?
The dog will stay within a yard of the owner.
Yeah, well, we want to make statements about the owner, so I can say I'm 68% confident that the owner is located between what? Where and where?
29 and 31?
Yeah, between 29 and 31. Okay. And even if I go down to 27 and 33, that doesn't give me 100% confidence either, okay? Because it is possible that this was just one of those strange times that the dog decided to pull more than 3 yards away from the owner. Okay. Can you guys see how I'm trying to relate this to the confidence interval stuff? Okay. So over here, what we have is we have the location of y bar. Okay. So when we're talking about confidence intervals, what we have is we have the samples information. Okay. We don't have the populations information. We don't know the mean of the population. But from the central limit theorem, we know that the sample mean follows the normal distribution, and that normal distribution has the center, or has a mean, equal to the population mean. So from the central limit theorem, we know that y bar, the sample mean, behaves kind of like the dog. It stays close to the location of the population mean. Even if we don't know where the population mean is, by knowing where the sample mean is, we can kind of infer where the population mean is. So analogous would be the dog's location is like the y bar that we see. Okay? Okay, and the owner's location and the behavior of the dog is the central limit theorem. Stating that y bar follows the normal distribution. Okay, so let's make this applicable to the thing that we're going for. Okay, so earlier I said that we have a random sample. Okay, 10 people were randomly selected. The mean of these 10 people is 104. The standard deviation is 13.6. Okay? So if we go to, if we look at the normal distribution, okay, and I want to shade the middle 95%, where would my z-score cutoffs be if I want the middle 95%? Well, the amount, how much would I want in this tail over here, and how much would I want in this tail over here? I would want 0.025, right? And 0.025. And so if I look this up in the z table, I would see that the z-score that gives me 0.025 is negative 1.96 and positive 1.96 over here. Okay? And so we know the sampling distribution of y bar has a standard deviation of, or standard deviation equal to, from the sampling distribution stuff that we did earlier, do you remember? Sigma over the square root of n, right? So I can then make a statement like, if I have y bar, I can say I am 95% confident that the population mean mu is between, and what I would do is I would take y bar and I would go down 1.96 sigma over the square root of n, and y bar plus 1.96 sigma over the square root of n. Does this make sense? So this is essentially what we did with the dog, right? We said we're confident that the dog is between, I mean, the owner is between, 95% confident the owner is between 28 and 32. Essentially, you were just doing plus 2 yards minus 2 yards. And here I'm saying we're going up, not exactly 2, but 1.96 standard deviations, and I'm going down 1.96 standard deviations. Does that feel okay? There is one slight problem, and can you guys see it? So if I wanted to take the information from my sample and plug it in here to get my answer, what is the problem that I'm going to run into?
To take the square root of, like, 10.
No, that's not the problem. It's not the problem that I get a weird number. Okay, let's see. Y bar is 104. N is 10. What's sigma? That's the population standard deviation. Do I have the population standard deviation? No, I only have the sample standard deviation. Okay? So we run into a problem. Okay? This thing requires that we know the population standard deviation. Okay? But that's kind of the whole point of us doing this thing, is that we don't know anything about the population. Okay? We only know things about the sample. So this is what we're going to do. We're going to just guess what the population standard deviation is. Okay? And so what would you say our best guess for the population standard deviation is?
Can't you just calculate it?
Well, we can't really calculate it. I mean, all we have is the only thing that we have that tells us about the population is my sample of 10 people, and all I have is a mean of 104 and a standard deviation of 13.6. So I'm going to argue that right now my best guess for the population standard deviation is my sample standard deviation of 13.6. Okay, but I have no idea if this is a good or bad estimate. Okay. But that's what I'm going to do. This is kind of, it's better than just saying I'm going to pick a random number from the sky. At least this seems like a reasonable number to kind of use. Okay, but it could be off. It could be too big. It could be too small. So we're going to replace sigma with S. Okay, but now I'm introducing an extra element of uncertainty. And so to compensate for that, I'm going to kind of give myself a little bit of breathing room, okay? And to do that, I'm going to change this number from 1.96 to something a little bit bigger, okay? And so now I'm going to introduce something called the t-distribution. So the t-distribution has a very interesting history, and you can go on Wikipedia and look up the t-distribution, but there was a quality control guy at the Guinness Brewery in Ireland, and he was trying to use statistics to figure out quality control, and in the beginning he was using the normal distribution, but he realized that he was running into problems, and he had to start kind of tweaking the normal distribution, but he wasn't quite sure. And so he did a lot of work kind of by hand. He did this brute force calculation of the t-distribution, of this new distribution, which he didn't have a name for. And he published a paper under a pseudonym called Student, and it was called Student's t-distribution. But anyway, it's neat. So we're going to adjust this number, 1.96, to something a little bit bigger, okay? And the t-distribution has something called degrees of freedom, and I don't feel like going into the explanation of what degrees of freedom is, but basically, if you have a very large sample, the amount of compensation you need to do is going to be less, because the large sample should give you a very good idea of what the population standard deviation is. On the other hand, if you have a small sample, you'll probably need to give yourself extra breathing room, because the small sample standard deviation is much more likely to be quite different from the population standard deviation. I mean, it could be close, but the probability that the small standard deviation is different from the population standard deviation is much greater than has a much greater risk than that of a large sample. Does that make sense? So a large sample should give you a pretty good idea of what the population standard deviation is. A small sample, on the other hand, is not going to be as reliable. So that comes into play when we adjust this number. A large sample, we only have to adjust this a tiny bit. It might go to like 1.97 or something like that. On the other hand, a small sample will bump this up to like 2.2 or 2.3, something like that. Okay, so I'm going to go to the next slide. And so let me just summarize everything I said. Okay, one problem. Okay, we do not know value of sigma, the population standard deviation. Okay, so our current best guess is S, our sample's standard deviation. Okay, but this introduces additional uncertainty. So we will compensate by changing 1.96 to another number based on the t distribution. Okay, so your reference tables that you should have, the third page is the t distribution, or I guess the second sheet. So I'll let you guys finish copying all of this down. Okay, and so if we're going for the middle 95%, the amount that we want on each tail would be 2.5%, right? So we're going to look at this column 0.025 for the upper tail probability. Okay, and you can see that at the very bottom, it also says confidence level 95% at the very bottom of that thing. Okay, and here you see at infinity, with infinity degrees of freedom, we use 1.96, okay, which comes straight from the normal distribution. So the normal distribution says for 95% you use 1.96, and if you had a sample size of infinity, which means your sample size is your population, you don't need to do any compensation, you use 1.96. Okay, but anything less than that, anything less than infinity, which is going to be all real life situations, you're going to have a lower amount of degrees of freedom. And we can see that as the degrees of freedom decreases, the amount of compensation gets bigger and bigger and bigger until you get to the top where you only have 1 degree of freedom and you need a compensation factor of 12.7, which is kind of ridiculously large. Okay.
These are discrete variable distributions.
No, this is the t distribution, which is kind of like a compensated normal distribution. We've kind of inflated the normal distribution a tiny bit. Okay, so here, let me just kind of say degrees of freedom in our situation is going to be n minus 1. Okay, so let me just recap the information that we had from before. The sample mean that we had was 104. Our standard deviation, I think I wrote 13 point, what did I write, 13.6? Yeah, 13.6. And I had a sample size of 10. Okay. So now what I'm going to do is I'm going to go y bar. I'm going to say I am 95% confident that the population mean mu is between y bar minus, and I'm going to just put in a placeholder, t star, meaning this number comes from the t table, and we're going to do s over the square root of n, and y bar plus t star times s over the square root of n. Okay, and so t star, so instead of 1.96 I'm using t star, and so t star comes from the t table. Okay, with degrees of freedom equal to n minus 1 and the confidence level of our choice. So in our case, we chose 95% confidence. This is kind of the standard number that we go to, but if you want higher or lower levels of confidence, that's up to you. So in our case, we have how many degrees of freedom? 9 degrees of freedom, okay? So I would go to my table and I would look at the column for 95%, which is this one right here, and I would go to 9 degrees of freedom, and I see that the number that I use is not 1.96 but 2.262. Okay, so I will use, so I use T star equal to 2.262 from the T table. Okay, and so my confidence interval goes from 104 minus 2.262 times 13.6 over the square root of 10, and 104 plus 2.262 times 13.6 over the square root of 10. Okay, so I have 104 plus or minus 9.73. Okay, or so 104 minus 9.73, what is that? 94.27. And 104 plus 9.73 gives me 113.73. Okay, so I'm going to say something like, I am 95% confident that the population mean is between 94.27 and 113.73. And we can say that from just this little bit of information. We take a random sample of 10 people, we get an average of this, standard deviation of this, and based on that, we can then make a statement about the mean of the entire population and say, I'm 95% confident that the mean of the entire population is between this number and this number. Yes?
So, because I see that it says like 104 plus or minus 9.73.
Uh-huh.
So isn't the 9.73 some sort of standard deviation?
So this is what we call the margin of error. Okay? So the and I'll label all of these things in a minute here. Okay? So the margin of error is a combination of the standard deviation of the sampling distribution, which we also call the standard error, and our kind of compensation factor, the T star, okay, which is known as a critical value. Okay, and I'll label all of these in a moment here. But I just want to make sure that this statement that I'm writing, I am 95% confident that the population mean is between, 94.27 and 113.73, that's okay. And how we got there is also okay. So this is our first taste of inference, and it comes, kind of as a culmination of our understanding of sampling distributions and our description of data with using just the mean and standard deviation here. Okay, so let me label the parts of a confidence interval. Okay. So a confidence interval will be bounded by y bar plus or minus t star times s over the square root of n. Okay, and this is a confidence interval for mu. Okay, so I should write, because we'll learn another confidence interval next week. Okay, so y bar, this is what we call the point estimate of mu. So when we take a sample and we calculate the sample mean, that sample mean kind of serves as a rough estimate of what the population mean is. Okay, we took a sample and we got the sample mean as 104. It's kind of a rough estimate for what the population mean is. In the same way that when you see the location of the dog, it's kind of, your safest bet is to think that the owner is located near the dog. Okay? So when you see y bar, your initial point estimate for mu is around there. But then you give yourself this plus or minus term, okay? And so individually, the t star, this is called our critical value. And s over the square root of n, this is our standard error. Or it's also the sampling, the standard deviation of the sampling distribution. Okay, and together, t star times s over the square root of n, this is called the margin of error. Okay, and so, during election season, they'll report figures like, candidate blah blah blah, is polling favorably with, at 54% with a margin of error of 2% or something like that. Okay, and so that's because they've conducted some kind of survey, and so statistically there's a margin of error, plus or minus, and they'll report that. And usually they choose 95% confidence or something around there. Okay. Okay, so this is our confidence interval, and we make a statement. Okay, our statement goes something like this. Is I am blank % confident that the population mean mu is between blank and blank. Okay, again, all of these things determined by your equation for the confidence interval. Okay. And it might be tempting to do this, but don't do this, okay? So in the previous example, we said, I'm 95% confident that the population mean IQ score is between, I forget, 94 point, what was it?
94.27.
94.27 and 113.73, okay? Do not say there is a 95% probability that mu is between 94.27 and 113.73. Okay? So don't say this. Why can we not say this? Okay? So here we're using the word probability. All right? And so let me try to illustrate the point here. Oh no, where did my coin go? Does someone have a coin? No, okay, I got one, All right, so I have a quarter right here. I'm gonna flip it here. All right, so I'm gonna just ask you a very simple question. When I flip the coin, what's the probability that it will land heads? And you say 0.5, right? Okay. So I'm gonna flip it right here. All right. I'm going to ask you, what is the probability that it landed heads?
Still 0.5.
Okay, all right. And now watch this. Now I'm looking at the coin, and I see how it landed, and I cover it back up. And I'm asking you now, what is the probability that it landed heads?
Well, we have to calculate the probability of lying.
I'm not lying. Okay.
68.
I haven't said anything. Okay. So I know how it landed. Okay. And I'm asking you a question. What's the probability that it landed heads? Okay. And you should have said, wait, because now there's no uncertainty. So it either landed heads or it didn't land heads. You don't know how it landed. I know how it landed. Okay, but you don't know. And there's now no uncertainty associated with the coin flip. Okay? So probability only makes sense when we're talking about things that have uncertainty with them. Before I flipped the coin, it made sense to say the probability that it landed heads, or that it will land heads, is 0.5. But once it landed, there's now no more probability associated with it. It either landed heads or it didn't land heads.
So now it's
Now it's
a confidence.
Yeah. So now, it doesn't make sense to talk about probability anymore. So it doesn't make sense for you to say there's a 50% probability that it landed heads. Okay. It now only makes sense to say, for you guys to say, I am 50% confident that it landed heads. Okay. Is that distinction clear? Okay. Well, and this is the frequentist approach to probability. If you've taken future class in probability and you learn the Bayesian way, then they talk about everybody can say 50% probability. Okay. But from the frequentist perspective, you guys cannot say there's a 50% probability that it landed heads because it either did or it didn't. You can only say I'm 50% confident that it landed heads. Okay? In the same way, the population mean, mu, is either inside this interval or it's not. Okay? We treat the population mean mu as a fixed quantity. There's nothing random about it. It's a property of the population. There's no uncertainty. We just don't know what it is. So it doesn't make sense to talk about probability. It's just we don't know what it is, so we can only talk about being confident that mu is in our interval or not. So don't say there's a probability of mu. It's only about our confidence about the location of mu. Is that good with you guys? It landed tails, by the way, if you guys care. But so again, yeah, probability only it only makes sense to talk about probability when there's uncertainty in an event, and there's no uncertainty regarding the value of mu.
Uncertainty meaning we can't know because it hasn't happened, whereas we still have uncertainty because we don't know what happened.
Yeah, we're not omniscient, so there's an uncertainty there. But yeah, there's not uncertainty in that the mean of the population is subject to random events. Okay, so mu, I mean, if we talked about the mean height of the population, technically, like if we could freeze time right now, it's not subject to random events, right? But because people are being born and dying kind of frequently, it's hard for us to say. But if we ignore that, mu is not subject to random events. Okay, so I guess I'll just write talk about the outcome. Okay, and then it's maybe I'll list off other things not to say. Okay, basically we are making a statement about the population mean. We're not making a statement about sample means, so don't say anything like, you know, I am blank % confident or etc. that the sample mean is between blank and blank. Oh, so I should write do not say. Okay, and we don't say this because we know the value of the sample mean, right? We know so we know the sample mean is 104. There's no uncertainty there. Okay, you know, don't say anything blah 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 that future samples or future values or future whatever, okay, will be between blank and blank. Okay, it's our statements are only about the population mean, nothing about the future. And say nothing okay. But confidence intervals are incredibly useful, okay, because from a sample, and you know, just even like a medium-sized sample, we can start making statements about the value of the population mean. Okay. And we can also make statements like, based on our sample, so we can make statements like ... based on our sample or our data and confidence interval, we have evidence that the population mean is not blank. Okay? So our confidence interval, so our 95% confidence interval for mu is from, what was it, 94.27 to 113.73. Okay, I think that's what we have. Well, whatever it was, let's just work with this. Okay, so based on this confidence interval, we have evidence that the population mean is not any number outside of the interval. Okay, so we have evidence that the population mean is not 114. Okay, or we have evidence that the population mean is not 93.7 or something like that, because these numbers are not inside my confidence interval. So this confidence interval is kind of a range of plausible values of mu, and any value outside of that we can kind of say is not plausible, or is not, we have evidence that it's not that thing. Okay? On the other hand, if somebody asked, do you have evidence that it's not 100? Our answer would be no. Okay? It doesn't prove, our confidence interval doesn't prove that the mean is 100. It just says we don't have any reason to believe that it's not 100. Is that okay? So you can't, our confidence interval will not provide evidence that it is 100, but it does not provide evidence against the belief that it's 100.
Can you use like mean and the complement of mean?
So the complement only can be used for events, probability events. Okay, so the mean itself is not an event. So there's no such thing as a complement to a mean because it's not an event. But you can have the event that I can't think of an event off the top of my head. Yeah. But so let me also write this other thing down. Okay, so on the other hand, our confidence interval does not provide evidence against the claim that mu equals 100, because 100 is within the interval. Okay, it does not prove, but it does not provide evidence that it is 100 though. That mu is 100. So we just have no reason to to reject the claim that it's 100. Okay, and so let's, I want to explore this even further, and I don't want to, you know, beat this to death or anything, but so let's look at this. Okay, so we looked at our confidence interval, and we did 104 minus 2.262 times 13.6. Okay, let's say we wanted to, we're going to take the same data, okay, same data. So we have y bar equal to 104, standard deviation at 13.6, and equal to 10, okay? And so our 95% confidence interval goes from 94.27 to 113.73, okay? What if I said, now make a 99% confidence interval? Okay, so I'll put the formula up there. Y plus or minus t star times s over the square root of n. Okay, so actually this will be a good exercise. Why don't you guys do this? Take a minute to make a 99% confidence interval for the population mean mu. So I'll pause the video right here. Okay, so looking around, it looks like a lot of you guys, maybe you don't have the final numbers, but you're on the right track here. Okay, so pretty much all of the numbers are exactly the same. The only thing that changes is our selection of t star, right? So I'm still using 13.6 over the square root of 10, and t star is now something else. So for t star, I'm going to look up 99% confidence. Okay, 99% confidence, and I have 9 degrees of freedom. So I'm going to use 3.250. Okay, 3.250. That corresponds to 99% confidence, not 99.9. Okay, so we're just going to make a 99% confidence interval, and I'm going to use 3.250. Can you guys see that? So that's my t star. Okay, so all I'm going to do is I'm going to do 3.250 times 13.6 divided by the square root of 10, and I get 13.98. So basically I have 104 plus or minus 13.98. So I'll do 104 plus 13.98. I get 117.98. And let's do 104 minus 13.98. And I get 90.02. Okay, so what do we notice about our confidence interval? The 99% confidence interval, how does that compare to our 95% confidence interval? It's bigger, right? It covers a wider spot, okay? So our 99% confidence interval is wider than our 95% confidence interval. So, well, let me just note. We use t star uses 9 degrees of freedom with 99% confidence. 3.250. Okay, and that makes sense if we think about it, right? If we want to be more confident about creating a zone where some unknown thing is, we should make that zone bigger if we want to be very confident. On the other hand, creating a zone that's too big is not very useful, okay? I can always say I'm 100% confident that mu is between negative infinity and positive infinity. That's not a very useful confidence interval, okay? Or even, you know, saying it's between 0 and 1 billion, still not very useful to us. So we have to, there's a balance between creating a very wide interval where we're very confident and creating too narrow of an interval where we're not confident enough. But this also points out an interesting thing, right? So whereas before, if I said, based on our 95% confidence interval, I said, do we have evidence that mu is not 114? You would say yes. With the 95% confidence interval, you would say yes, I have evidence that it's not 114. But for the 99% confidence interval, what do you have to say now? You have to say, I don't have evidence that it's not 114. 114 is within my interval. So what's the deal there? How can I have, I'm using the exact same data here. And here I'm saying, you know, here we say, we have evidence mu is not 114, right? Because 114 is outside of my interval. But over here, okay, now I say, you know, we do not have evidence that mu, or we do not have evidence, against. We do not have evidence against the claim that mu is 114. Okay, so what's going on? I'm using the exact same data. Over here, I'm claiming that I've got evidence that it's not 114, and over here I'm saying I don't have evidence against that claim. Yeah, so the thing is I'm changing my confidence level. Okay? So over here, somebody says, do you have evidence that it's not 114? You're saying, yes, I've got evidence that it's not 114. And they say, how certain are you? You'd say, well, my evidence is based, my claim, or my statement is based on a 95% confidence interval. So I'm 95% confident about my statement. Okay? On the other hand, they might say, well, what if you wanted to be more confident? What if you wanted to be 99% confident? Now, you can't make such a bold statement anymore. Okay? So now we have to say, if I want to be 99% confident, then I can no longer claim that I have evidence against 114. Okay, so if you want to be really confident about your statements, about saying stuff like it is or it isn't this, okay, if you want to be really confident, you're not going to be able to say as much. You're going to need, you know, a lot more data or something like that. So when we change our confidence level, if we want to be really confident, we're going to be kind of rejecting these things less often. How does all this feel? Feels okay? Okay, well, we'll end today's lesson there then. You guys have a quiz next week. I've tried to detail kind of the things you need to know for next week's quiz. And we'll see you guys next week.